bromine, iodine. These gases are evolved at anode. Next is, if a sulfate is present and chloride is present, nitrate is present, or carbonate is present. So here, what is the reaction at the anode? That reaction takes place at anode. In this case, 2H2O gives O2 plus 4OH, 2OH minus. O2 plus 2OH minus. By losing of electrons, here it loses electrons. In this case, it loses electrons, and what is this? Oxygen is evolved in this reaction. So always in cathode, these metals are present, more active metals are present. Hydrogen is evolved at the cathode, and this what is that? Chlorine, bromine is present, and in this case, oxygen is evolved, and sulfate, chloride, nitrate, this carbonate are present, then oxygen is evolved at the anode. Okay. So next we take example. If you use an electrolysis reaction, electrolysis of K2SO4. To take example, Al2SO4 taken place aqueous solution to use. Okay. Copper sulfate, copper chloride, sodium chloride. So when we use this electrolytes, which electrode is used here? Platinum. What is the platinum electrode? It is the inert electrode is used in this case. So K2SO4 aqueous solution when electrolyzed, hydrogen is evolved at cathode, and anode, what is the reaction here? O2 is evolved at the anode. Al2SO4 taken place is electrolyzed. What is the compound here? Hydrogen and oxygen. When aqueous copper sulfate is electrolyzed, copper and oxygen is evolved at cathode and anode. If you use the aqueous copper chloride, copper and chlorine, and if you use aqueous NaCl, what is the compound? We get H2 and Cl2. These are the compounds evolved at cathode and anode in electrolysis reaction. Next is use copper sulfate by using of copper electrodes, not inert. If you use the active electrodes, so at the cathode, copper is evolved. At anode, again anode also copper is evolved. If you use the NaCl with the mercury electrode, mercury as the electrode, we get sodium amalgam and chlorine gas is evolved. So here, if you use a active metals in electrodes anode, that active metal only evolved at anode. Here, if you use a copper instead of sulfate, copper shows more tendency to lose electrons. So copper is evolved at anode, and the copper ions reduced and convert, and copper deposited at a cathode. So these are different types of compounds evolved at anode and cathode in electrolysis reaction. Next, so this electrolysis reaction, what is that? Metals are called as this metals, electrodes, metal conductors. So conductors are two types here. Conductors, metals, metallic conductors, or we can call it as a electronic conductors, or solid state solid conductors. So what is the electrodes we use in this reactions? Like platinum, graphite, these are called as a metallic, electronic, or solid conductors. And in this case, conductivity increases with decrease in temperature, and conductivity increases with increase in valency, valency of metal or valence electrons of metal, and the conductivity depends on structure also. Depends on structure of metal also. Here, in the structure of metal, metal contains the sharp edges, conductivity is more, and liquid state of conductors are called as a liquid state of conductors are called electrolytes. Liquid state of conductors are called electrolytes. So here, what are electrolytes? Different types of electrolytes here. Electrolytes are, what is electrolytes? Aqueous acids, aqueous bases, aqueous or molten salts, which are called as a electrolytes. And what is the conductivity? Because of mobile ions, electrolytes again, what is the divide into strong and weak electrolytes? So strong electrolytes, strong acids, example, mineral acids. Acids of IA6A group are called as a mineral acids like HCl, HNO3, H2SO4, we can call it as a mineral acids. And strong bases like NaOH, 1A, 2A group elements. 1A, 2A group elements can form strong bases. And the salts of the strong acids and strong bases. Salts of strong acids and strong bases like KCl. So in this case, strong electrolytes alpha value. What is alpha? Degree of dissociation is always greater than 1. But in case of weak electrolytes, what are weak electrolytes? Generally, if any acid contains a carbon, that is always a weak acid. And what is the basis of D block elements? Ammonium hydroxide. These are called as a weak acids and weak bases. Both are involved in reaction. We get salts of weak acids and weak bases. So these are called as a weak electrolytes. So for weak electrolytes, alpha value less than 1. Alpha is called as a degree of dissociation. And here, electrolytes conductivity, electrolytes conductivity can be influenced by what type of factors? What are factors influence the conductivity of this electrolytes? First is concentration. Concentration increases, conductivity decreases. So dilution of this electrolyte increases, conductivity generally increases. And next is the small size of ion, more hydrated or solvated. So conductivity decreases and charge increases, conductivity decreases because it is more hydrated, and is viscosity increases and conductivity always decreases. Melting point, what is the temperature increases, so conductivity always increases. So here in electrolytes, liquid state of conductors, when concentration increases, conductivity decreases. When dilution increases, conductivity increases. When size of ion decreases, it is more surrounded by water molecules. So ionic mobility decreases and conductivity decreases. When charge of ion increases, conductivity decreases, because when charge increases, again it is more surrounded by water molecules or any polar solvent. And when viscosity increases, conductivity decreases. temperature increases, ionic mobility increases, so conductivity also increases. So for electrolytic conductors, what is the relation, quantitative relation between amount of substance deposited and how much electricity is passed? That can be explained by what is that Faraday's laws. There are two laws are there, two Faraday's laws are there. Faraday law 1 and Faraday's law 2. First we start with Faraday's laws. First law, first we start with the first law. Okay. So what is this Faraday's first law? It explains a quantitative relation between amount of substance deposited and how much amount of electricity is passed into that solution. According to Faraday's first law, weight of substance deposited is directly proportional to current in coulombs. So if you pass, this is a coulomb is the strength of current. If we pass more amount of current and more amount of substance is deposited, and here Q is equal to current in coulombs. What is this? It is the current in coulombs, and Q is equal to IT. What is I? Current in amperes. T is equal to time in seconds. So here we write instead of Q, we can write W is equal to IT also. And we write here one constant, EIT. What is EIT? E is equal to, we can call it as a electrochemical equivalent. So W is equal to, we can write EQ. E is equal to W by Q. So what is the indicator? What is E value? What is E definition? If 1 coulomb of electricity, 1 coulomb of electricity is passed, how much amount of substance deposited in grams? That is called as a electrochemical equivalent. If 1 coulomb of electricity is passed, how much amount of substance deposited? That is called as a electrochemical equivalent. So here we write so this is a W is equal to EIT or EQ by 96,500. That is equal to EQ by 96,500. What is this E? E is called as a chemical equivalent. E is equal to atomic weight. Atomic weight by valency. So W is equal to, right here, atomic weight by valency into current in amperes into time in seconds by 96,500 coulombs. This is a what is called Faraday's first law, or here W by E is equal to W by E is equal to Q by 96,500, or that is equal to IT by 96,500. And from this, number of gram equivalence, number of gram equivalents. Here we write now. This side we write according to Faraday's law. Number of gram equivalent of substance deposited. Number of gram equivalents of substance deposited is equal to number of Faradays. Number of gram equivalents is equal to moles into N. N factor valency, that is equal to, again we write the number of Faradays. Okay. So this is the Faraday's first law. What is Faraday's first law? Weight of a substance directly proportional to strength of current in coulombs. Again, strength of current in coulombs is equal to current in amperes into time in seconds. So here W is equal to, we can write proportional to IT, or we can write W is equal to EIT. E is called as a electrochemical equivalent, or we can write W is equal to EQ, or we write here W is equal to EIT by 96,500 coulombs, that is 1 Faraday, or we can write EQ by 96,500, or we write here weight by equivalent weight is equal to Q by 96,500, it is equal to IT by 96,500. Next is number of gram equivalents of substance deposited, always equal to number of Faradays, or number of gram equivalents also we can write into moles into valency of that metal, or we can call it as the N factor. N factor, that is also equal to, what is that number of Faradays. So it is a Faraday's first law. Next is Faraday's second law. So according to Faraday's second law, the same electricity is passed through different electrolytic cells. So what is the weight of a substance deposited? That is directly proportional to equivalent weight of that substance. Okay, when we pass same amount of electricity through different electrolytic cells, what is the amount of substance deposited is directly proportional to equivalent weight of substance, that is called as a Faraday's second law. Okay. So if he explains about relation between weight of substance deposited and equivalent weight of substance. Next is the current efficiency. Current efficiency is equal to number of Faradays of current utilized by total number of Faradays of current passed into 100. Or we can write actual mass of substance deposited by theoretical mass of substance into 100. Current efficiency. And gram equivalents of substance deposited is equal to current efficiency, what is the number of Faradays into current efficiency by 100. So this is the what is the information related to current efficiency. So what is this current efficiency? It depends on how much amount of current is passed and how much amount of current is utilized in a reaction, that is the current efficiency. Okay. After that, next Ohm's law. Okay. So according to this resistance, which obstructs the flow of current directly proportional to length of between two electrodes and the area of cross section according to Ohm's law, or we write R is equal to rho. R is equal to rho L by A. R is equal to rho L by A. What is this, Nana? R units. Ohms. Ohm is the unit of R, and rho is called as a, that is that specific resistance. What is specific resistance? Rho is equal to RA by L. Right here, if you take a small cube, okay, volume is 1 cubic centimeter, and in that 1 ml of electrolyte is present. Distance between electrodes constant, area of cross section fixed, but we don't know concentration of electrolyte. Okay, in that what is the resistance of that resistant in that electrolytic solution? That is called as a specific resistance. What is the units of specific resistance? Ohm is the area by length, ohm centimeter or ohm meters. Next is the, in that 1 cubic centimeter of that cube, 1 ml of electrolyte is present. In that, what is the conductivity? That is called as a specific conductivity K. What is that? It is called specific conductivity, that is equal to 1 by rho, or we can write here 1 by R into L by A, and 1 by R we can write it as a G, because G is equal to 1 by R. What is G? This is called as a conductance. Conductance and units. What are units? Reciprocal of ohm or Siemens. These are the units of conductance. K is called as the specific conductance, or we can call it as a conductivity, indicated by kappa. So 1 by R is equal to conductivity. L by A is called as the cell constant. L by A. What is that cell constant here? We indicated by this star mark. That is L by A. L by A is called as a cell constant. And what are the units of kappa? That is the specific conductance. Units 1 by R. That is reciprocal of ohm. L by A, that is per meter, or we can write Siemens per meter. Okay, so this is called as a specific conductivity. Rho is called as a specific resistance. In case of rho and K, what is that distance between electrodes? Say there is no change, fixed area of cross section fixed, but volume also fixed, but what is that the concentration of electrolyte is unknown. It may different. How to find out cell constant? How to find out a cell constant? Okay. In this method, we take a electrolytic cell which contains two platinum electrodes. One electrode is connected to positive, other electrode is connected to negative. And in this, what is that known K? Known K of KCl. We know that kappa, that is the conductivity of KCl solution or specific conductance of KCl solution that is placed in this vessel. And what is the distance is L, area of cross section L that we find. Okay. So first we use a Wheatstone bridge. It is connected to Wheatstone bridge. It is connected to Wheatstone bridge. From this Wheatstone bridge, we can find out a resistance, and from that resistance, we can find out the conductivity. Okay, and it contains a Wheatstone bridge contains one detector, audible detector, and it is connected to AC current. AC current, and what is this AC current? 500 to 5500 hertz of AC current is used. That is converted. This detector is converted AC current into audible frequency, and it is R1. R1 means this is connected to R1 is resistance because of this known K of KCl solution. This is R2. So we can adjust this. We can call variable resistance. R2 is the variable resistance. Unknown is R3 and R4. Unknown, what is the known resistance is R3, R4. Known is R3, R4. R2 is the variable resistance. We can adjust, and R1 is the what is the resistance of this electrolytic cell, and we find out the R1. R1 is equal to R2, R4 by R3. So here we find out a resistance, and we know K value because KCl K value already know, conductivity value already know. So we know that K is equal to 1 by R into L by A. We know this value, K value we know, 1 by R value know. From that we can find out a cell constant. So K is equal to G into G star. Cell constant is equal to K by G. So in this method, in this way, you can find out a cell constant of electrolytic cell. You can find out the cell constant of that electrolytic cell. Next is molar conductivity. Molar conductivity. What is the specific conductivity? Molar conductivity is equal to K into volume. We know that specific conductivity, the volume is 1 ml only, or fixed only. But the molar conductivity volume is not fixed. And in specific conductivity, we don't know concentration. But in molar conductivity, we know concentration of that electrolytic solution. And distance between electrodes is fixed. but area of a cross section is not, what is it, not fixed. It is a large enough area of cross section so that whole solution, total electrolytic solution is present in between two electrodes. What is the specific conductivity? Area cross section of electrodes fixed. Concentration we don't know. Concentration and distance between electrodes also fixed. Volume also fixed. But in case of molar conductivity, we know concentration of electrolyte that is fixed. Area of cross section is fixed. What is distance is fixed. Area of cross section is large enough. So whole, what is the, we don't know volume, the total volume of electrolyte is accommodated in between two electrodes. So that is called as a molar conductivity. So if you use 1 mole of electrolytes, what is the molarity? Number of moles into 1000 by volume in milliliters. We know that. But what is this here? N is equal to 1 mole of electrolyte is present. Then what is volume? Volume in milliliters, that is equal to 1000 by molarity. So we can write here K into 1000 by molarity. So what are the units? Siemens centimeter square per mole reciprocal of moles. This is called as a molar conductivity. The same way, in case of normality, we use equivalent conductivity. So K into 1000 by normality. Here Siemens meter or centimeter square per number of equivalents. Gram equivalents of electrolyte. So this is a molar and equivalent conductivity. Next is effect of dilution on conductivity. Effect of dilution on conductivity. So what is effect of dilution on conductivity? With a dilution, molar equivalent conductivity always increases because molar or equivalent conductivity directly proportional to volume. When dilution increases, dissociation of electrolyte increases. So more ions are present and that more ions show more conductivity. And the specific conductivity volume is fixed. Volume is fixed. With increase in dilution, in that volume, number of ions increases, but in that volume, number of ions always decreases. So K, number of ions decreases in that volume. So when the K increases, what is this? Conductivity. What is the volume increases? When volume increases, K value always decreases because in that particular area, number of ions decreases because of dilution. Okay, next is molar or equivalent conductivity of when we compare with weak electrolytes. Okay, if we draw graph, so molar conductivity, take example, and here we write delta C, root C. What is this? Root C indicates C is the concentration, or we can write C 1 by 2. Here, the dilution is infinite dilution. This is the dilution is infinite dilution, and conductivity is called as a limiting molar conductivity here, and here concentration is 0. Dilution is infinite, so the total number of ions are completely dissociated. So after the dilution, dissociation is not possible, and it is a strong electrolyte and it is a weak electrolyte like a CH3COOH. So weak electrolyte, it is difficult to find out molar conductivity because the weak electrolyte at infinite dilution. At infinite dilution also, it is what is that? It is not possible to dissociate. But a strong electrolyte with infinite dilution completely dissociated, their concentration is 0. So at infinite dilution, so this is a conductivity. So molar conductivity at that concentration is equal to at infinite dilution minus B root C. This is the Debye-Hückel equation. It is applicable to strong electrolytes. B is the constant. B is constant. But in case of weak electrolytes, how to find out? For this, we use a Kohlrausch law. What is that? Here we use a Kohlrausch law. So according to Kohlrausch law, it is mainly applicable for or to find out conductivity of weak electrolytes. According to Kohlrausch law, conductivity of any electrolyte, you take NaCl is equal to what is the conductivity of sodium ions plus conductivity of Cl minus. If you take a 1 molarity concentration of NaCl, the same way 1 molarity concentration of KCl, conductivity of K plus and conductivity of Cl minus. But in these two cases, conductivity of chlorine is same. Means conductivity of one ion, same ion is present in different electrolytes, that does not influenced by other ions. That is the Kohlrausch law. So with the help of this, we can find out conductivity of weak electrolytes. Example, conductivity of acetic acid, how to find out? It is not completely dissociated. So here, that is equal to use a conductivity of CH3COONA plus the conductivity of HCl minus conductivity of NaCl. So from this, we can find out conductivity of CH3COOH. So here it is dissociated into CH3CO minus and Na plus, because it is a salt of strong base and weak acid, so it is completely dissociated. HCl is strong acid. It is also dissociated into H plus Cl minus. NaCl is also strong electrolyte, dissociated into Na plus minus, Na plus plus, or we can write here minus conductivity of Cl minus. So from this we get the conductivity of acetate ions and H plus ions. And also we can find out alpha value also. Conductivity at that concentration, conductivity at infinite dilution. This is the alpha degree of dissociation. Also we can calculate from Kohlrausch law. Okay. So one example we discussed here. From previous questions, 2Fe plus 3 plus 2I minus 1 gives 2Fe plus 2 plus I2. E0 cell is equal to 0.24 volts at 298 Kelvin. Find out standard Gibbs energy of that reaction. Standard Gibbs energy of that reaction. Find out what is the standard Gibbs energy of that reaction. What is the standard Gibbs energy of the reaction? Delta G0 is equal to minus NFE. We know that. How many electrons are transferred here? 2, 3 is the plus 6, plus 4. Here also minus 2, 0. So 2 electrons are transferred in this reaction. So we write -2, F is equal to 96,500. E naught value is given 0.24 volts. So this is a direct question. It is a previous question, an entrance exam question. So from this we can find out that delta G value, that is 46.32 kilojoules per mole. Next question. For a cell involving one electron, E naught cell is equal to 0.59 volts at 298 Kelvin. The K for cell reaction is, find out the value. Is given that 2.303 active by NF is equal to 0.059 volts at 298 Kelvin. Find out K value. So we know that when K is given, E is equal to, E naught is equal to 2.303 active by NF log K. N is 1, F is 1 Faraday. So 298 Kelvin, this value is given, total value also given. This is 0.59 log K. So log K is equal to 0.59 by 0.059, that is equal to 10. What is that? We get the 10 value. K is equal to anti-log of 10, that is equal to 1 into 10 to the power of 10. The correct answer. Next question. The molar conductivity of a 0.5 mole per decimeter cube of AgNO3 with electrolytic conductivity of 5.76 into 10 to the power of -61 per centimeter at 298 Kelvin piece. This is the question. What information is given here? Find out the molar conductivity. So what is this here? Conductivity is given. Conductivity is given. Molarity also given. Is the concentration of AgNO3. So molar conductivity is equal to 5.76 into 10 to the power of -3 into 0.5 by 1000. Direct question it is 1000, 0.5 into 1000 by molarity is 0.5. So what is the value we get? 11.52 Siemens centimeter square per mole, reciprocal of mole. Next question. At 25 degrees Celsius, molar conductance of 0.1 molarity aqueous solution of ammonium hydroxide is 9.54, and at infinite dilution its molar conductance is 238 ohms, reciprocal of ohms centimeter square per mole minus 1, reciprocal of ohms. Find out the alpha value. This is the question. What is alpha? Alpha is equal to conductance at that concentration by conductance at infinite dilution. Okay. So what is the value we get here? 9.54 by 238. So from this, we can find out the conductivity at infinite dilution also. Next question. The 2012 question lines. One question here. Molar conductivity is at infinite dilution of NaCl is 126.4, HCl that is 425.9, CH3COO that is 91. So find out the molar conductivity for CH3COOH at infinite dilution. So find out what is the molar conductivity at infinite dilution. So molar conductivity at infinite dilution is equal to molar conductivity of CH3CONA plus conductivity of HCl minus conductivity of NaCl. So what is the value here? 91 plus 425.9 minus 126.4. From that we get the conductivity at infinite dilution. How many grams of cobalt metal will be deposited in the solution of cobalt 2 chloride is electrolyzed with the current of in amperes per 109 minutes. Cobalt atomic weight is given 59. So it is based on Faraday's first law. Then the question again. Cobalt dichloride, cobalt charge is +2. Weight of substance deposited is equal to TREIS-IT by 96,500 is equal to atomic weight 59 by 2 into current in amperes. What is the current in amperes? 10 amperes into 109 minutes, we convert into 60 seconds by 96,500. From that, we get a weight of substance deposited that is almost equal to 20 grams. The electrode potentials for copper +2, if electron gives copper +1 and copper +1 plus electron gives copper, or plus 0.15 volts and plus 0.50 volts. The value of E naught of copper +2 by copper. Here, when both are added, we get that this value. Copper +2 plus electron gives copper +1. Copper +1 plus electron gives copper. When both are added, what is the value we get? Copper +2 plus 2 electrons gives Cu. So this is the E1 value, it is the E2 value, and it is the E3 value. So you find out E3 value. What is the N E3 value? N E3 naught is equal to E1 N1 plus E2 N2, and this is N3, and E3 is equal to E1 naught N1 plus E2 naught N2 by N3. E1 naught, what is the E1 naught value? 0.15 into how many electrons are transferred in this case? 1 plus E2 is equal to 0.50. Again, 1 electron is transferred. In the third case, how many electrons are transferred? 2 electrons are transferred in this third case. So from that, we can find out what is that E3 value. What is the value we get here? From this, we get 0.325 volts. So these are few previous entrance exam questions, and we'll discuss it. We'll continue next class.